so I can put this up. All right, what are we taking a look at today? We are starting chapter 6. We just finished chapter 5 on probability. Now we're going to use that probability and some of those ideas with these things called random variables. Okay, and what these random variables do is, at first, they let us sort of get rid of simulations in a way. They're a more efficient way to look at many types of simulations. Once we have the random variable stuff down, terrifying. Once we have the random variable stuff down, we're going to look at the expected value of a random variable, or also known as the mean. And it wouldn't be good to look at the mean if we didn't look at the standard deviation, and that's your asynchronous assignment. You're looking at the standard deviation of discrete variables, Then you're going to look at continuous variables. So right now we're looking at discrete. Hopefully that word, you remember that. We did talk about what discrete means. That is like integers. There's space between your numbers. You don't take all the decimals in between the numbers. But first, random variables. All right, what can we do here? So here's a scenario where a random variable will be useful. So bottled water versus tap water. Do you think you can tell the difference between bottled water versus tap water? Man, I would love to do that experiment to see if you could. So can students tell the difference between bottled water and tap water? 6 students take on the challenge. Each student is given 3 unmarked cups of water, only one of which has bottled water. Suppose 4 students guess correctly. All right. Is that evidence that they can actually tell the difference? Or did they just get lucky? So how likely is it that 4 or more students would guess correctly if they were in fact just guessing and couldn't actually tell the difference? So this is a scenario where we normally do a simulation. All right, so here is my description of how to do a simulation. First, randomly pick 6 random numbers from 1 to 3. Then we would label. A 1 would represent a guessing correctly, and a 2 through 3 would be guessing incorrectly. So each time they would technically have a 1/3 chance of getting the correct answer. Okay? Because they have 3 cups, only 1 cup has actual bottled water in it. And then always say what you're going to record in a simulation. Record the number of correct guesses. And then we would see how likely is it that 4 people would get the correct answer just by guessing. All right. If it happened a lot in our simulation, well, then it's very possible they were just guessing and we don't have evidence that they can tell the difference. But if we never get 4 people guessing correctly in our simulation, well, that does give us evidence that they can tell the difference, because that outcome is not going to happen by chance alone. Now, that's tedious. All right, we got to generate random numbers. We have to do it over and over and over again. We have to record it over and over again. We have to make a dot plot to figure all this stuff out. It's kind of tedious. So instead, another option is to use what's called a random variable. All right, and it starts out super simple. We are very creative in math. Our random variable is going to be x. That's the way we roll. And we're going to say, all right, we're going to define our random variable as the number of students who guess correctly. Number of students who guess correctly. And then we can use probability to figure out how likely is it that many students would guess correctly. So this is a discrete variable because this variable x can either be a 0, 1, 2, 3, 4, 5, or a 6. It can only take on those values. No 1.5s. All right, we're not cutting people in half here or anything, okay? It's frowned upon. We have our discrete variable, and then we can calculate the probability of each of these events, each of these outcomes happening. Okay, so what is the probability that 0 people would get this correct? All right, so 0 people get it correct. There's an 8% chance that they all get it wrong. There's a 26% chance that only one person gets it right. 33% chance that 2 people get it right, and so on and so forth. Now, where do those numbers come from? You can't get there yet. I was able to calculate those numbers using what's called the binomial theorem. We'll get there in what, section 6.3, I do believe. But what we call this whole table is a probability distribution. It tells us the probability of every outcome of our random variable. So now we want to think, all right, what are the chances, what's the probability, that we'll have 4 or more people guess correctly? So what is the probability our random variable is bigger than or equal to 4? Well, that is all 3 of these, right? So 0.08 plus 0.016 plus 0.001. I forget what that number is. 0.08 plus 0.016 plus 0.001. 0.097. So there is a 9.7% chance that 4 students would just get the correct answer by simply guessing. Yeah, that's not a super definitive answer one way or another, sadly, but it's a fairly low chance. So I'd say there is some evidence that these kids can identify a bottled water versus tap water, because there's less than a 10% chance that they would get this by guessing. 4 out of the 6. So there's some evidence that they actually know the difference. That'd be a fun one to do together. But again, our new thing here, defining the random variable and then looking at using the probability distribution right there. Okay. All right, so in general, a random variable is simply a number that takes numerical values that describe outcomes of a random process. It describes outcomes of a random process. And today, right now, we're looking at discrete random variables. So like 0, 1, 2, 3, 4, 5, etc. Not the decimals in between. That is what discrete means. All right, so our first example here, to put it all together, anybody heard of APGAR scores before? If you were a little bit older when you had a sibling, you might have had or heard about APGAR scores. It's a score that they give to a baby at birth. So in 1952, Dr. Virginia APGAR suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and response when stimulated, which is a simple way of saying they pinch the baby. She developed a 0-1-2 scale to rate a newborn on each of the 5 criteria. A baby's APGAR score is the sum of all of those, which gives a whole number value from 0 to 10. Again, discrete number from 0 to 10. APGAR scores are still used today to evaluate the health of newborns. Although this procedure was later, this is kind of weird, later named for Dr. APGAR, the acronym APGAR also represents the 5 scales: appearance, pulse, grimace. They got a little creative there to make the acronym work. Activity and respiration. By the way, extra credit for anybody who can do that to my last name for statistics. All right, what does BOLT stand for in statistics? There's got to be something that you can make sound intelligent. You did a case study on it? That's awesome. I'm a bad father. I forgot the APGAR scores of my children. I'm sure it's really important that you remember that stuff, right? I think they were like 7 to 9-ish. They were decent. We didn't have any complications. We were pretty lucky, but I do not remember what their scores were. All right, what APGAR scores are typical? To find out, researchers recorded the APGAR scores of over 2 million newborn babies. Imagine selecting a newborn baby at the random. That's our random process. All right, so here is our random variable. X is equal to APGAR score. So we defined our random variable. The table gives the probability distribution. So here we have the probability of each APGAR score occurring. So if I pick one at random here, so 7, there is a 9.9% chance that a random baby will have a score of 7. Okay. All right. What questions are we trying to do here in specific? Write the event the baby has an APGAR score of 0 in terms of X. All right. Well, that's just X equals 0. All right. Our random variable is equal to 0. Then find its probability. So the way we write that is the probability of X equaling 0. And of course, because all textbooks are obnoxious, they don't tell us that one. So, but we have all the others. And so remember, all of these has to add up and equal to a total of 1. They all have to add up and equal a total of 1. And so we can just add them up, subtract from 1 to figure out this number. It is 0.001. I did it already. But add them up, subtract from 1. So the probability of an APGAR score of 0, which would be really, really bad, is 0.1%. B. Doctors decide that APGAR scores of 7 or higher, all right, 7 or higher, indicate a healthy newborn baby. What's the probability that a random selected newborn is healthy? All right, so first write that in probability notation. 7 or higher, so that means X is greater than or equal to 7. That is the weirdest alligator mouth I've ever drawn. There we go. 7 or higher there. So all we have to do is add those probabilities up. So 7 or higher would be these right here. Add those up. All right, so 0.099 plus 0.319 plus 0.437, 0.053. So 0.908. So there is a 90.8% chance that a randomly selected newborn baby is healthy. Now, I'm skipping over a little bit. But why did you add those 3 up? What probability rule did you use to add those up? All right. Yes, the fact that you can add those together is a probability rule, but hopefully it does make sense that you are allowed to add those together. All right, now that's all pretty easy, I'm hoping. The tricky part can sometimes be the fact that they don't make it always super obvious, this part right here. All right, they threw us a bone here and said, all right, we're going to make the first one easy. They said of 7 or higher, they made it very obvious what numbers to add up. It is possible to be a little more obtuse with that and not be quite so obvious. And so you do have to sometimes pay close attention to wording like at most blank, or is at least blank, or less than, or greater than. that can sometimes make it a little bit more difficult to figure out what probability you're doing, but you just need to read carefully, okay? So a baby with an APGAR score, next one, of less than 4 will need full resuscitation. All right, write this in probability notation and find the probability of it happening. So this is the probability of X is less than 4. Now, which numbers am I using then? There's no equal sign, so I don't include 4. So that's from 0 to 3. All right, that's the part where you want to read carefully. Do you include the end point or not? Okay, so that will be 0.001 plus 0.006 plus 0.007 plus 0.008. All right, 3 or less. But that is also less than 4, essentially. What does that become? I don't remember. 0.001 plus 0.006 plus 0.007 plus 0.008 is equal to 0.022. So that is a 2.2% chance that a randomly picked baby will need full resuscitation. Full resuscitation. Not too bad, I'm hoping. All right, time for some job prospects, all right? You ready for some job prospects? Anybody want to make lots of money? Here's an opportunity to make lots of money. Show me the money. Does anybody know what that's from? That is a really old reference. Bull, why do you pull out these old movie references like that? You probably have heard that, but you have no idea what movie it's from. Show me the money. So, you can do this for a living. Actuaries are the daring people who put a price on risk, and they definitely probably just sit in a cubicle, estimating the likelihood and costs of rare events so they can be insured. Has anybody ever heard of like celebrities or musicians or famous people that they insure different parts of their body? Like a violinist or a pianist might insure their hand for many thousands of dollars because if they break their hand or something, their livelihood is gone. Don't actors and actresses sometimes like insure their nose or something? I think. But you see those weird things on the internet sometimes. Got to be careful about the internet. But an actuary is the person that would determine how much to charge to insure all of those things. So that takes financial, statistical, and business skills. It also makes them invaluable to many businesses. Actuaries are rather rare themselves. It's kind of hard to become an actuary. You have to take an extremely difficult series of tests about probability and statistics and all kinds of stuff. Only about 19,000 work in North America. That is not very many. Because of this, they're paid well. So I looked at this one up. The median California salary is $114,000 a year. Dang. It's pretty good. That's the middle, right? Half make more, half make less. But the median salary is $114,000. Woo. Yeah, they are in demand, but it's a hard job to get into. So, what do they actually do? Well, they oftentimes do look at this thing called expected value, which is what we are going to look at right now. So a life insurance company pays policyholders $10,000 in case of death. So if you die, they pay your beneficiaries. They don't pay you. That would be kind of useless. You would be dead. But they pay your family $10,000 and $5,000 in case of disability. So if you do get disabled, they'll give you $5,000. A simplified case, true, but it is something important to do once you get older. The Bolts certainly did it. If I ever just disappear randomly, it was my wife that did it. All right, I'm worth $500,000 dead to my family. It sounds crazy to think about that. I'm worth $500,000. Whew. Yeah, so if Bolt just disappears, it was the wife. Now, we did that because it's an important thing to do when we were first starting our family. I was the only person working at the beginning. My wife was working part-time, but not enough to support everyone if I kicked the bucket, like, et cetera, et cetera. And so to make sure they were taken care of in the horrible circumstance, we got life insurance. And that would give her quite a few years of cushion before having to pay all the bills. So important to do, especially when you start a family. But an actuary's got to figure out, because the insurance company's still got to make money, because sometimes you are going to pay out the $10,000. Sometimes you are going to pay out the $5,000. You've got to balance it out to still make a profit. So the actuary would make something like this. This would be our probability distribution. So our random variable, X right here, is the payout. So we define the random variable. It can only take on 3 values in this simple case: $10,000, $5,000, or $0,000. All right, so only can take on 3 values. And they want to then calculate what's the average payout going to be. So they have to calculate the probability of each happening. So here there is a 0.1% chance of death, a 0.2% chance of disability, and a 99.7% chance of neither happening. So you're fine. Again, most people are fine, right? I'm not dead yet. Most people are fine. And so those will balance out the few larger payments you have to make. But how will they average out? So we call this expected value, E of X, because again, math people are creative. It is also the average, and so we do use the Greek. All right, mu. It's been a while since we've seen that, huh? Mu, again, is the average, the mean. So how do we calculate this average? It's actually quite easy. You take the value of X and you multiply it times the probability. Then you add that and you do it again. You multiply X times its probability, you add them together, and the last one as well. Multiply those together and add them up. What does that formula look like? It is the sum of each individual X, X sub I, times the probability of each individual X. So that's what the formula technically looks like, but it's pretty easy. So in this case, I'm going to take the 10 grand, 10,000, and I'm going to multiply it times 0.001. I'm going to keep doing that over and over. Now I'm going to take the disability one, so that is the 5,000, and I'm going to multiply it times 0.002. And the last one, even though it's kind of trivial because we're taking 0 times 0.997, and the 0 will make it cancel out, but I will still put it there. Run that all through your calculator, hit enter, and you will get the expected value, the average payout to each policy. Okay. Now, quick word, thankfully you actually don't need the parentheses. Your calculator does know the order of operations, so thankfully it will do the multiplication before the addition. So you can type that in without the parentheses, and you will be fine. But type, enter, and you get $20. So on average, they're going to pay out $20 to each policy. Now, that's an average. Are they actually giving anybody $20? Well, no. They only ever give out 5,000 or 10,000. But most people are getting 0. Those average out to be $20 a piece. So, what does this insurance company have to do to make money? Charge more than $20. If they charge $50 for a policy, they make, on average, $30 per person for this policy. So, that is expected value. Pretty easy to calculate. If you have a big data set, yes, it's a little tedious, but it's not that bad. All right, you add up multiplying the x times the probability. Not too bad. So, all right, take a break from bolt talking right now. Where's another place this is used? Insuring rockets. Kind of cool. So, I don't know if you saw in the news, but SpaceX did just launch some astronauts back into space, right? Was it yesterday? Day before, maybe? It was supposed to be Saturday, but it got scrubbed last minute, and I think it was yesterday. Those launches are insured. So if it blows up, all right, SpaceX does not have to just lose the $150 million. It's insured, and the insurance company would pay them that $150 million. Whew. What do you charge to insure a space rocket? Crazy. I'm going to throw this into the chat. I want you to take a minute, read this, so you can see kind of where this is actually used. It's kind of cool. It's not all about expected value or anything, but it is at least relevant and the same topic we're looking at. Give you 3-4 minutes. Give it a read. right, hopefully you got through a bit of that. I thought that was kind of cool. I was like, yeah, in the background of all that article is this idea of risk analysis, which is really the idea of a probability distribution for a random variable. All right. And Musk, that dude is freaking crazy. A visionary to be true, but he's off. It's fun to read about him sometimes. He's making the argument that, hey, look, my rockets are cheaper to insure. That must mean, the sub-language here, that an actuary has determined that it's less of a risk, so they can charge them less. And this other person's like, well, that's not quite the case just because SpaceX can do everything cheaper, so the insurance company is insuring less money, which is why the rate is cheaper. But the rate was the same, they said, 4%. So this company determined that to make it profitable for the insurance company to insure a rocket launch, they charge 4% of what the worth is. That's got to be kind of a high risk, high reward business. Now, life insurance is much less so, because life insurance, you get the law of large numbers. You insure so many people that, yeah, some people are definitely gonna die, and you'll have to pay out the 10 grand. Some people are definitely gonna get in a car accident and have a disability, and you'll have to pay out the 5 grand. But the law of large numbers lets you really accurately predict the true proportions of those happening, and that is what reality is going to match up with. And so pretty solidly that your expected value will be what you actually get. Rocket launches, you don't have a law of large numbers working on your side, so you might get super unlucky, and your first 2 launches will be the equivalent of death, and they'll blow up, and you'll have to pay out the huge sums, and you won't necessarily have the thousands and thousands of good launches to balance out and then make money. High risk, high reward stuff there. I thought that was kind of cool. All right, let's practice this a little bit more, ladies and gentlemen. We got to make sure we can write a probability distribution and then calculate the expected value. All right, so head on back to the OneNote to me here if you're not back away from the website. Let's take a look at 2 more examples here. So a carnival game offers a $100 cash prize for anyone who can break a balloon by throwing a dart at it. It costs $5 to play, and you are willing to spend up to $20 to try and win. You estimate you have about a 10% chance of hitting the balloon on any throw. And let's assume that if you hit it, it'll pop it. Although, man, I was at the Fresno Fair once. I threw that dart. I swear it hit the balloon and just bounced off. And I was like, really? Really? So if you ever play this game, make sure you take that dart real quick and rub it on the cement to sharpen it up a bit. Make sure it's nice and sharp. Then go ahead and do it, because I definitely had a dart bounce off the balloon once. I was pissed. All right, so we think we have a 10% chance of hitting the balloon. Create a probability distribution. So, first define the random variable x. What is x going to represent? So what do we really care about here? We care about how much money we will win. So that's going to be our random variable. So how much money will we win? Well, if we win on the first throw, we make $95. Because remember, we paid $5 to play, then we won on the first throw, so we get $100. It matches up to $95. So what are the chances of winning on your first throw? Well, 10%. We said that we figure we have a 10% chance of hitting the balloon. So there's a 10% chance we will win $95. All right, but if we don't, we might win on the second one. Well, if we win on the second throw, now we only make $90. All right, now what is the probability of that happening? This is where it gets a little weird. Okay, we have to use our probability rules. So the probability of winning on the second throw means you missed the first throw. There was a 90% chance of missing on the first throw. But then you hit the second throw, and there was a 10% chance that you hit the second throw. Okay, these are independent events. We are doing the probability of A and B. All right, and the probability of A and B is the probability of A times the probability of B. These are independent, so we get to use this simpler one. If they were not independent, we'd have to use the general multiplication rule, but these are independent events, so I can use the simple one. All right, third throw, I only make $85. Now, how does that third throw happen? What is this outcome's probability? Well, I missed twice, so 0.90 times 0.90. Those are my two misses. And then don't have two misses. That's illegal. Times 0.10. Your third shot you make. Fourth one. All right, we still haven't spent all our money. We said we'd spend up to $20, and now we have spent $20. This is our last shot. All right. So that'll be 0.90 times 0.90 times 0.90 times 0.10. So we missed our first three and we hit the last one. And of course, though it is very possible we miss all of them, but we call it a day. We lose $20. We lose $20. What is the chances of that happening? Well, that means we missed every time. So that is 90 to the fourth power. I don't want to write it out 4 times. So 90 to the fourth power is that probability. If you want to see what those actually are, sometimes it helps to actually put the probability down. So 0.9 times 0.1. Oops, turn your calculator on, Bolt. It works better. So this is a 9% chance. This is an 8% chance. This is a 7% chance. And 0.9 to the fourth power is a 65% chance. So there's a 65% chance we don't hit any balloons and we lose $20. There's a 10% chance for the first one, a 9% chance, an 8% chance, a 7% chance, etc. So we finished our probability distribution. Time for the expected value. So the expected value of x, again, is the same thing as the average. I'm going to put both of those just as a reminder. And we simply multiply each probability times the value of x. And we add them all up. Okay? Everybody practice this for a second. That way doing it will help keep it in your head. Dust off your calculator if you lost it. All right? Use your phone calculator if you need to. Multiply those out. 729. And you should get $17 and about 20 cents, it looks like. 20 cents. It rounds up. So if we did this over and over and over again, on average, we would make $17.20. It's actually not very good for the carny. They might want to rethink their balloon placement. I'm guessing the probability of winning is not quite 10% on the balloon dart throwing. Otherwise, they'd be losing money. Or they'd have to lower their prize. I don't think the balloon dart throwing game gives you $100. I think you get a big teddy bear, which is probably actually only worth $3 or something like that. So that would also be a way to help the carny out, is not to give away $100 for hitting the balloon. That would definitely lower the expected value that they would have to pay out. Because technically this would be worth it for you. On average, you'd make $17 if you were able to do it over and over and over again. All right. Yeah, we got time for one more, ladies and gents. One more. But why do you keep gambling? It's like you're trying to teach us how to gamble. Hey, don't do it. The casino always wins. All right. Betting with the teacher. We'll see if anybody wants to take me up on this offer. I had 2 people do it in third period. No, 3. And so I had 3 people do it in third period. Your crafty teacher makes every student in class a simple offer. Roll an 8-sided dice. The octahedron of chance. If you roll an 8, you get 5 extra credit points. If you roll anything else, you get to roll again. If the second roll is 3 or higher, you get 2 extra credit points still. Whoa. If the second roll is not 3 or higher, though, you lose a point. Create a probability distribution for this scenario and interpret the expected value. All right, let's do this. So I had to figure out what is our random variable here going to be. And so what are we interested in? The number of points. How many points is Bolt given away to students? So I've got 3 different outcomes. You could get 5 points, you could get 2 points, or you could lose a point. What is the probability of each? So the probability of getting 5 points. Well, the only way to get 5 points is to roll an 8 on your first go. All right, that's the least likely, right? You have a 1 out of 8 chance of getting 5 points. Now, the next one. The next one is where it gets kind of tricky. What is the probability on your second roll of getting a 3 or higher? Now, this outcome, though, is the probability, remember, of A and B. So first, you had to roll something that was not an 8. That is a 7/8 chance that you will first roll something that is not an 8. Otherwise, you never even would have gotten here. Times, now what is the probability of rolling a 3 or higher? So how many options? 3, 4, 5, 6, 7, 8. So we got 6 options. So 6 possibilities out of 8 would then get you your 2 points. All right, now, how could you lose a point? Well, it's not a third roll. That's, I think, what might throw people. It's not a third roll. You still have a 7/8 chance of missing your first one. So that's the same. But now on your second one, you don't get 3 or higher. You get a 1 or a 2. So that would be 2 out of 8. That would be the probability of getting a -1. Woo, dangerous. So our expected value, again, you just multiply these. Multiply, 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 and add them up. What does that give us? So 5 times 1/8 plus 2 times 7/8 times 6/8 plus, and don't forget -1, -1 times 7/8 times 2/8 gives us an expected value of 1.718. So that means on average, over many different students trying this out, on average, I would give away 1.718 points, which means on average, I'm giving away points, not taking away points. So overall, people's grades would go up. But that's not very much comfort to this poor person right here who gets the -1. Well, yeah, but your friend got 2 points. Well, yeah, but I lost 1. Yeah, but your friend got 5 points. Yeah, but I lost 1. Remember, the average is what happens over long periods of time. Not always a big comfort for individual results. Anybody feeling lucky and they wanna play? Anybody feeling lucky? If you roll an 8, you get 5. All right, Alejandro's got this. Here we go. All right, Alejandro's first. Where's my random number? You ready for this? You may not trust me, but how do I know this is going to be the right numbers? All right, I'll go back. All right, so I'm going to generate one random integer from 1 to 8. All right, I'm not lying to you. From 1 to 8. All right, Alejandro, this one's yours. Ooh, you got a 3 first. All right, you still have a chance. Remember, you still have a chance. Hey, you got a 5 the second time. So you get 2 points. Alejandro, well played. Have a good day, sir. Isaac, you ready? This one's for you. Ooh, all right, didn't get the 5. Drum roll. Oh, but he got a 3 or higher. Also got 2 points. Look at that. Not bad. All right, Rebecca, you ready for this? You better want it. Here it goes. Oh, a 2. Dang it. All right, didn't get the 5. Try again. Ooh, we got the 2 points. Woo. Barely. All right. So far, so good. Jessica's up next. Ooh, the 2. All right, no one's gotten the 5 points yet. Next. Ooh, a 6. All right, we're down for another 2 points. Madeline's up next. We got some gamblers here. A 3. All right, too bad. All right, but one more time. A 3 again. It did refresh there. It's just another 3. That's why we couldn't tell. All right, that's 2 points still, though. No losers. Look at this. All right, Maria wants it. 2. Darn it. All right, and click. A 6. We got another 2. Wow, no losers. Third period got angry because the third person lost. We've done what? 5, 6 people? No losers yet. Nice. So far, our real life values are a bit higher than our expected values. Oh man, now everyone's feeling the juice. I'm like, boy, I gotta have it. Oh no. 3, too bad. And I did click it, so it's another 3, which means you get 2 points, right? Man, I'm too lenient. I gotta worsen these odds. Maybe I'll make the odds worse, but the payoff more. Maybe that's what I should do. But no, I was hoping. How many times do I have to get a loser? I need a loser. All right, 2. They didn't get the first one. 8. They got the second. Well, that's still only 2 points, even if you get an 8 the second time. Good stuff there, ladies and gentlemen. All right. It's lunchtime. So, what should you be able to do right now? All right, make a probability distribution. Interpret what those mean. And then find the expected value and interpret what that means. Okay? Those are the two things we got to be able to do. Your video here today expands on that. If we're going to do the mean, we got to do the standard deviation, right? So your video is on standard deviation, and then going from discrete random variables to continuous random variables. Hopefully right now, this is not you. We're almost done with the week, ladies and gentlemen. Then we get some vacation. All right, everybody. Have yourself a great, great day. I will see you all, Thursday? Yeah. Oh, real quick plug. It's Kindness Week, right? So, send your teachers a nice note, but I'm going to give you the challenge. All right? Quick plug. Think about your freshman teachers. All right? Freshman teachers get no love. I know I was a freshman teacher once. Everybody remembers their senior teachers, okay? Nobody remembers their freshman teachers. I want to give you the challenge right now. Think back to your freshman year. Send your freshman teacher, one of them, a nice note. Be like, hey, look, thank you for being cool back in 9th grade. I'm now doing great as a senior. Tell them about yourself. Tell them something cool you did, etc., etc. All right? There's my challenge for you. Say something nice to your freshman teachers.